This is Dr.S.Prasanna, Assistant Professor of Mathematics in Pingle Government College for Women. I am dealing with the topic linear algebra for BSc final year mathematics. This is a topic in CBSE system in SEM 5. And today's class is about the null space, a theorem based on the null space and some problems based on that theorem. Okay, recall the term null space, which we have gone through the definition of null space in the previous video lessons. The null space, we have seen that it is an important concept in the linear algebra, in the study of linear algebra. Now let us prove a theorem based on the null space. This theorem states that the null space of an m by n matrix is a subspace of Rn. This statement can be defined in three ways. Three statements mean the same thing. They give the same meaning, but I am giving them in a different manner. The terminology is different, how we say the statement is different, but the meaning of the statement, whatever be the way it is told, is the same. So the first way of the statement is the null space of an m by n matrix is a subspace of Rn, or let A be an m by n matrix, then the null space of A is a subspace of Rn, and the set of all solutions, this is the another way of telling the statement, that is the set of all solutions to a system Ax bar is equal to 0 bar of m homogeneous linear equations in n unknowns is a subspace of Rn. So the set of all solutions to a system Ax bar is equal to 0 bar, and this Ax bar is equal to 0 bar is a system consisting of m number of homogeneous linear equations, and all these equations are in n unknowns, and this is a subspace of Rn. Now let us move on to prove this theorem, and for that I need a matrix of order m by n. So I have taken a matrix A of order m by n. So let A be an m by n matrix. Now if we are given a matrix of order m by n, we can define the null space of that matrix, and that null space of matrix A is denoted by null A, and it is defined as null A is equal to set of x bar such that Ax bar is equal to 0 bar. That means null A is a set consisting of the vectors of the form Ax bar, which are column vectors. We can see x bar are column vectors of the order n by 1. And these column vectors, when commuted to the given matrix A, if they give rise to 0 bar, then all such column vectors are the elements of the set null A. That means null A consists of all n by 1 column vectors which satisfy the equation Ax bar is equal to 0 bar. So here I have taken the set null A, which is defined as null A is equal to set of x bar such that Ax bar is equal to 0 bar is the set null A, it is represented by equation number 1, and this gives the implication that each element of null A has n rows and 1 column. As I said, the elements of null A are column vectors of order n by 1, and hence null A is a subset of Rn. So Rn is this n-dimensional space wherein it consists of all the column vectors of the order n by 1. And null A is also a set which consists of n by 1 column vectors which satisfy the equation Ax bar is equal to 0 bar. And hence null A is a subset of Rn. Now our aim is to prove that null A is a subspace of Rn. Now we have seen that null A is a subset of Rn, and to prove that null A is a subspace of Rn, we need to prove three conditions. And the first condition is that the zero vector, we have to show that the zero vector 0 bar is in the set null A, and that means null A consists of the zero vector. And the second condition says that if u bar comma v bar are any two vectors in null A, then their sum, that is sum of two vectors u bar plus v bar, is also in null A. That is the second condition. And the third condition states that if u bar is any vector in null A and C is any scalar, then we have to prove that null A is a subspace of Rn. We have to prove that C u bar, the scalar multiple of u bar by the scalar C, is also in null A. So C u bar, if we show that C u bar is also in null A, then we are through. That means that shows that null A is a subspace of Rn. So to prove all these three conditions, let us first start with the condition that 0 bar is an element of null A. That is an obvious thing, because 0 bar, which is a column vector in this context we can consider 0 bar as a n by 1 column vector. Then 0 bar consists of all zero elements, all entries as zeros, and it is a n by 1 column vector. And as null A consists of all the n by 1 column vectors which satisfy the equation Ax bar is equal to 0 bar, here in place of x bar, if we take 0 bar, then we can have A0 bar is equal to 0 bar. That means capital A, which is a matrix of order m by n, when multiplied to 0 bar, which is a column vector of order n by 1, gives rise to again a 0 vector of order m by 1. So m by n matrix multiplied to n by 1 matrix gives you m by 1 matrix. So that is how we can see all the column vectors of order 0 by 1 belong to null A. So null A is a subset of Rn. So null A is a subset of Rn, and 0 bar, which is a column vector of order n by 1, is in null A. That means null A is a non-empty subset of Rn. Already we know that null A is a subset of Rn. After knowing that the zero vector 0 bar is in null A, we can say that null A is a non-empty subset of Rn. So now consider to moving on to the next condition, second condition, to prove that the sum of, and that means vector addition, exists in null A. For that we need at least two vectors. So consider two vectors u bar comma v bar belongs to null A. Then as u bar belongs to null A, by the definition of null A we can say that au bar is equal to 0 bar, because in equation 1 we said that null A consists of all the elements x bar such that Ax bar is equal to 0 bar. Now as u bar is in null A, we can say that by equation 1 au bar is equal to 0 bar. Similarly, as v bar is also, as we are taking v bar as also an element of null A, we can say that by equation 1 a v bar is equal to 0 bar. So u bar comma v bar, if these two are elements in null A, then we can say that au bar is equal to 0 bar and av bar is equal to 0 bar. These two we can say by using the equation 1. Now consider A times capital A into u bar plus v bar. And this is further equal to au bar plus av bar. This we can do by using the distributive property of matrix multiplication. As the set of all matrices satisfy the distributive property, that means the distributive property exists in matrix multiplication, and using that we can say that capital A times u bar plus v bar is equal to au bar plus av bar. And by above statement we can see au bar is equal to 0 bar and av bar is also equal to 0 bar. Now substituting those two in this step, we get au bar, a times u bar plus v bar is equal to 0 bar plus 0 bar, and 0 bar plus 0 bar is nothing but equal to 0 bar. So now we could prove that capital A times u bar plus v bar is equal to 0 bar. That means u bar plus v bar when multiplied to the matrix A is giving rise to the 0 vector. But this is the condition which should be satisfied for a column vector to be in the set null A. So a times u bar plus v bar is equal to 0 bar gives us the thing that u bar plus v bar belongs to null A. So u bar plus v bar is an element of the set null A. Now let us, that means we have in this second bit we could prove that the sum of two vectors which are in null A is again in null A. That means addition of vectors is existing in null A. That is what we have proved by true. Now let us move on to prove the condition 3 in the set null A. For this condition we need two things. One is a scalar and the other one is a vector. So I have taken a scalar c and a vector u bar. Now I said that let c be any scalar, and I have considered capital A times c u bar. C u bar means it is the scalar multiple of the vector u bar by the scalar c. Now I am considering A times c u bar, and this we can write as c times au bar, for the reason that c is a scalar, and in matrix, by the definition of matrix multiplication by a scalar, we can write a into c as a into cu bar as c times au bar. So using the property of scalar multiplication in matrices, we can write a cu bar as c times au bar. Now au bar, as we have already seen in the bit 2, that whenever u bar is a vector in null A, then au bar is becoming 0 by the definition of null A. So u bar is a vector in null A means it satisfies the condition in null A, that is ax bar is equal to 0 bar, and hence au bar is equal to 0 bar. And now c times au bar we can write it as c0 bar. This is by the reason that au bar is equal to 0 bar, as u bar is an element of null A. Now this is further equal to c0 bar, we can write it as simply 0 bar. And now what is that we have arrived at? Let us see. Capital A times cu bar is equal to 0 bar. This is what we got. So this means cu bar when multiplied to the matrix A is giving rise to the 0 vector. This means cu bar is an element of null A by the definition of null A in equation 1. Therefore cu bar belongs to null A. So in bit 1 we have proved that the 0 vector 0 bar is in null A, as A 0 bar is equal to 0 bar is an obvious thing. And in 2 we have proved that if we consider two vectors u bar comma v bar in the set null A, then we can see u bar plus v bar is again in null A. And in 3 we have seen that if C is any scalar, then Cu bar is also in null A. So from 1, 2 and 3 we can conclude that null A is a subspace of Rn. So this is that is how we could prove the theorem, and hence the theorem is proved. So the statement of the theorem is the null space of an m by n matrix is a subspace of Rn. This is what we proved now. So this can also be stated as, let A be an m by n matrix, then the null space of A is a subspace of Rn. The same statement can also be stated as the set of all solutions to a system A x bar is equal to 0 bar of m homogeneous linear equations in n unknowns is a subspace of Rn. So this is the theorem we have proved now, and using this theorem, based on this theorem, we can solve some problems. In fact, these the problems we are going to solve can either be solved by using this theorem, or we can make use of another theorem that we have proved in earlier classes, which states that if v1 bar and v2 bar are in vector space V, then capital H is equal to span of v1 bar comma v2 bar is a subspace of V. So either of these two theorems can be used to solve these problems. So to show you, in the first problem I have solved it by using two methods, in both the methods. In one method I have taken the above theorem to solve the problem. I have made use of the above theorem to solve the problem, and in method 2 I have made use of the theorem that we have proved earlier, which I read now for you. And let us go through this problem now. So if W is equal to set consisting of the column vectors A, B, C such that A minus 3B minus C is equal to 0, then show that W is a subspace of R3. So W is a set given like this, and we are asked to show that W is a subspace of R3. As W, we can see here W is consisting of all 3 by 1 column vectors. If those are 3 by 1 column vectors, that means 3 by 1 matrices. So all the 3 by 1 column vectors are the elements of the three-dimensional space of real numbers, which is denoted as R3. So we can say that W is a subset of R3 by seeing the definition of W. Now let us move on to the solution now, and as I said, I want to prove this, I want to solve this problem in two ways, and in the method 1, I want to solve this problem by using the above theorem which we have proved just now. So see this method 1. Here I am directly saying that W is a subspace of R3. This is what we have to show in this problem, and I am claiming directly in the first step itself that W is a subspace of R3, and then I am proceeding to justify my statement that W is a subspace of R3 by giving some reasons. And how I am justifying myself is that since W is the set of all solutions of the non-homogeneous system of linear equations, and here in the definition of W, we can see that W consists of all the column vectors of order 3 by 1, which are of the form A, B, C. Are the such column vectors are, if they have to be in W, the set W, then they should satisfy the equation A minus 3B minus C is equal to 0. But A minus 3B minus C is equal to 0 is a system of linear equations which are non-homogeneous, and here actually the system is consisting of three variables, namely A comma B comma C. But here in the definition of W, we are given only single equation A minus 3B minus C is equal to 0, and hence that itself, that equation, the single equation itself represents the system of linear equations, homogeneous linear equations in A comma B comma C. And this system of equations, whatever be the solutions of this system of equations, the set of all those solutions is the set W that is given to us in the problem. And hence we can say that W consists of all the 3 by 1 column vectors satisfying the equation A minus 3B minus C is equal to 0. And hence we can say that W is a subset of R3. So first of all, W is a subset of R3, and all the equations, all the solutions that satisfy that given single equation, it has only one solution, that is given as 1 minus 3 minus 1, and this is the column vector of order 1 by 3. It can be written as a column vector as 1 minus 3 minus 1. Then we can see that it satisfies the equation, and we can say that it is the W is a subspace, null space, consisting of the matrix 1 by 3 matrix 1 minus 3 minus 1. Then W is the null space of R3, because already we have seen that W is a subset of R3, and now we can see that W is the null space of R3, where that null space consists of the matrix 1 by 3 matrix, which is given as 1 minus 3 minus 1 as a single row 3 columned matrix. And if this is the null space of R3, a null space of W, then W is a subspace of R3 by the statement of above theorem. Hence, by above theorem, W is a subspace of R3. So this is little bit complicated to prove this theorem, solve this solve this problem using above theorem. But using the another theorem, the solving this problem is a bit easier. So let us move on to the method 2, wherein I have used another theorem which states that if V1 bar and V2 bar are in vector space V, then H is equal to span of V1 bar comma V2 bar is a subspace of V. So to use that theorem, first of all, let us consider what is given to us. We are given that W is equal to set consisting of the column vectors A, B, C, such that A minus 3B minus C is equal to 0. Now consider that equation. Consider A minus 3B minus C is equal to 0. Now solving this equation for the leading variable A in terms of free variables B and C, we want to remain these two. We want to take these two variables B and C as independent variables, and A as a dependent variable depending on the variables B and C, and that is how B and C are free variables and A is a variable depending on B and C. By writing the above equation as A is equal to 3B plus C, we can say that B and C are free variables and A is a variable depending on B and C. then the vector ABC, the column vector ABC, that is a matrix ABC, can be written as 3b plus c, b, c. And here we can see by taking b common as a writing b as a scalar multiple, we can write the vector beside it as 3, 1, 0, as the coefficients of b in this vector are 3, 1 and 0. And similarly, plus taking c as a scalar multiple, we can write it as c times 1, 0, 1, as c has the coefficients 1, 0, 1 in this column vector. So 3b plus c, b, c can be written as b times 310 plus c times 101. Now I want to take these two column vectors as v1 bar and v2 bar, and that is why here I have mentioned it as let v1 bar is equal to 310 comma v2 bar is equal to 101. Then we can say that by above statement ABC, the column vector ABC is equal to B V1 bar plus C V2 bar, that is equal to linear combination of vectors V1 bar comma V2 bar. So this is the linear, as it is a linear combination of vectors V1 bar comma V2 bar, it is in the span, or this vector ABC is in the span of V1 bar comma V2 bar. As ABC is an arbitrary element of W, we can say that any element of W is a linear combination of vectors v1 and v2, and that is how W is equal to span of v1 bar comma v2 bar. So that can also be written as W is equal to span of the vectors consisting of the set consisting of two vectors 310 comma 101. So when by this theorem, whenever v1 bar and v2 bar are any two vectors in a vector space V, then a set which is H which is a span of v1 bar comma v2 bar is a subspace of V. And using this theorem, here also we can see W is equal to span of v1 bar comma v2 bar, and that is how W is a subspace of R3. So in this problem, we have seen both the methods, where in the first method I have used above theorem that we have proved today, and in the second method I have used this theorem which we have proved in the earlier video lessons. Now let us move on to the second problem. If W is equal to the set consisting of the column vector A, B, C such that A, B, C are the variables satisfying the equation A plus B plus C is equal to 2, such that A plus B, A comma B comma C are real numbers, and these A, B, C are real numbers and they satisfy the equation A plus B plus C is equal to 2, and hence we can say that W is a subset of R3 because it consists of all the 3 by 1 column vectors satisfying that given equation A plus B plus C is equal to 2. Now in this problem this W is given like this, and we are asked to determine whether the given set W is a vector space or not. W is a vector space means W is a subspace of R3, and if it is a subspace then it automatically means that it is a vector space. So to prove that W is a vector space or not, we have to see that whether W is a subspace of R3 or not. So to prove that, to see that or to determine that, we have to make use of this above theorem, where the theorem states that if v1 bar and v2 bar are in vector space V, then H is equal to span of v1 bar v2 bar is a subspace of V. But whatever be the theorem we are making use of, we should always remember that the zero vector should be in the set W. Then only W can be shown as a subspace or vector space. So here let us first of all consider the given set W, and W is given as the column vector ABC such that ABC variables satisfy the equation A plus B plus C is equal to 2, and ABC are the real numbers. Now consider that equation A plus B plus C is equal to 2. Actually this is also a homogeneous system of linear non-homogeneous. This is non-homogeneous system of linear equations in variables A comma B comma C. Now that equation can be rewritten as A is equal to 2 minus B minus C. Then the column vector A B C can be written as 2 minus B minus C B C, and that is further equal to 2 0 0 0. 2 0 0 is one vector that we can write separately, and the plus B times the another vector that we can take write besides B as minus 1 1 0. As we can see, the coefficients of B in this vector are minus 1 1 and 0. Similarly, plus C times it is minus 1 0 1, because C has the coefficients minus 1 0 1 in the left hand side vector. But of course we could be able to write ABC as a linear combination, but we should be cautious about the condition that the zero vector should always be in that set W, to show that W is a subspace or vector space. So let us see whether this zero vector is in W or not. Here I can say that W do not consist of the zero vector, for the reason that if A is equal to 0, B is equal to 0, C is equal to 0, or if we take all the variables as values 0, then we can see that 0 0 0 0, that solution do not satisfy the equation A plus B plus C is equal to 2, because 0 plus 0 plus 0 is not equal to 2. So that is how ABC can never be equal to 0 bar. That means even though ABC can be written as linear combination of some vectors, but 0 bar is not in W. That is how the zero vector is not in W means we can say that W is not a subspace of R3, even though W is a subset of R3 as it consists of 3 by 1 column vectors. But here we can see that W cannot be a subspace of R3, as the condition of subspace, among the three conditions of subspace, the first condition where the zero vector should exist in that W is not satisfied here. So as the condition of subspace is not satisfied, we should say that W is not a subspace of R3. Now let us move on to the next problem. That is again a problem wherein we are given a set W, and we are asked to determine whether the given set W is a vector space or not. That means we have to see that whether W is a subspace or not. And here W is defined as, in the problem, the definition of W is given as the set consisting of the column vectors RST, where RST are the variables here, and here we can see those are taken from the set capital R, those are real numbers, and those variables satisfy the equation 5R minus 1 is equal to S plus 2T. So this is the single equation given here, and it is also a non-homogeneous equation in non-homogeneous linear equation in the variables R, S, T. This single actually to get the values of three variables we need three equations, but here also we are given a single equation, and that single equation we can see rearranging that equation. First of all, consider the given set W to write the solution. First of all, write the set given to us. Then it is W is equal to set consisting of the column vectors R, S, T, such that 5R minus 1 is equal to S plus 2T is the equation given to us, and it is mentioned that R, S, T belongs to capital R. Here I missed to write smaller, but we should suppose that R, S, T, the three variables are real numbers. Now, here this equation 5R minus 1 is equal to S plus 2T is the single non-homogeneous linear equation given to us. By solving this equation, we cannot get the values of R, S, T, because if we have to solve for three variables, then we definitely need three equations. But here, as it is a single equation given to us, just rewrite it and see whether it can be linear, it can be a homogeneous equation or non-homogeneous equation. Rewrite it and see. Here consider 5R minus 1 is equal to S plus 2T, and this we can see 5R minus S is equal to 5R minus S minus 2T is equal to 1. I have taken the two terms, S term and T term, to the left hand side, and minus 1, the constant, is taken to the right hand side. Now we can see that the equation has now become as 5R minus S minus 2T is equal to 1. Here we can see that this is an equation in three variables R, S, T, and it is equal to 1. So this is a non-homogeneous and linear equation, and this is the single equation given to us. Now, as in the above problem, here also I can write either R or S or T as a linear combination, and we can write R, S, T, the column vector R, S, T, as a linear combination of two or more vectors. But by the experience in the above problem, we have seen that even though if we write that vector ABC as a linear combination, after that we have seen that the zero vector is not in W. So in this problem, first of all, let's verify whether zero vector is in W. Then we can move on to write. If zero bar is a vector in W, then we can move on to write W as a linear vector, column vector in W as a linear combination of two or more vectors, one or two or more vectors. So let us see whether zero vector is in W first of all. So if I take R is equal to 0, S is equal to 0, T is equal to 0, all the three variables as the real number 0, then we can see that these values do not satisfy the equation given to us, that is 5R minus S minus 2T is equal to 1, because 5 into 0 minus 2 into 0, the left hand side becomes 0, but the right hand side is 1. So 0 can never be equal to 1. So this is an absurd. Therefore, R is equal to 0, S is equal to 0, T is equal to 0 is not possible. That means RST, the column vector RST can never be equal to the 0 vector 3 by 1 0 vector 0 0 0. That means RST is not equal to the 0 vector 0 bar. That means 0 here also, as in the above problem, here also we can see that the 0 vector 0 bar is not an element of W. If 0 vector is not in W, there is no question of telling that W is a subspace, because in the necessary and sufficient conditions of subspace includes the 0 vector to be in that set. So the existence of 0 vector in this set W is not satisfied, and hence W cannot be a subspace of R3. Why have I taken this set R3? Because R3 is the three-dimensional set of real space, vector space of real numbers, where it consists of all 3 by 1 column vectors. Here also, by in the definition of W in the problem, we can see W is also consisting of all 3 by 1 column vectors. That is how W is a subset of R3. But we couldn't prove that W is a subspace of R3, because the non-existence of the 0 vector in W shows that W is not a subspace of R3. So this is all about a theorem and some problems based on theorem that we have proved earlier. So the theorem we have proved today is a null space of an m by n matrix is always a subspace of Rn, where Rn is the n-dimensional space of space consisting of n by 1 column vectors of real numbers. So this is what we did in this today's lesson. So with this I close the class now. So we shall see some more problems in the next video lesson. Thank you.